Thanks a lot for coming to this talk. That's a pretty big crowd, no pressure at all. So let's get started. Short introduction. I always say short introduction, then I go on for 2 minutes. Deepu K Sasidh, I'm the co-lead of JHipster and a Java champion. I created a bunch of OSS tools like K-Dash, JDL Studio, and so on. I'm an open source aficionado, polyglot developer. I work as a developer advocate at Okta, focusing on the Auth0 product. I frequently publish about languages on my blog, so do check it out if you're interested. You can follow me on these socials. I also have a chronic tendency to keep saying in between, every now and then, so please bear with me. So, concurrency in Java. So threads are an integral part of the Java language, right? It has been, Java has had good multi-threading support from the early ages, right? From its early days. So the concurrency capabilities in Java evolved slowly. And Java is quite good at using multi-threaded CPUs and multi-core CPUs. So concurrency has always been one of the strong aspects of Java. So let's see how the concurrency support evolved in Java. So, multi-threading was supported by Java from version 1 onwards. Before JDK 1.1, Java had even support for green threads. That was in version 1.0. So, also known as user mode threads. But the feature was removed in JDK 1.1, as the implementation was not any better than platform threads, and with 1.1 we had platform threads. So the green threads were removed in favor of platform threads. We'll see why the implementation was not good, or how it is better now and everything later. So JDK 1.1 had basic support for platform threads, or operating system, or OS threads, whatever you want to call it. And JDK 1.5 had more utilities and updates which improved concurrency and multi-threading. So JDK 8, 1.8, brought in streams, completable feature, asynchronous programming support, and a lot more concurrency improvements. I think so. After 1.1, probably 1.8 had the most significant improvements around that. But again, nothing groundbreaking or nothing extremely noteworthy. So, while things continue to improve over multiple versions, as I mentioned, there has been nothing groundbreaking, in the concurrency aspects for the last three decades. Like the concurrency model in Java, that is not to say that the concurrency model in Java is not good or not powerful. The concurrency model in Java is quite powerful and flexible, right? It may not be the easiest to use if you compare to some modern languages, but it is still quite flexible. You can do almost everything that you need to do. Developer experience could be a bit of a problem. That is primarily due to the shared state concurrency model that is used by default. And combine this with the mutable aspect of Java objects, you could have issues, especially when you're trying to synchronize. You could have data races and these kinds. So these were the issues around Java threading that we normally see, and that is one reason people normally don't have a very good impression of Java threading. Of course, if you're using a lot of Java threading with the current model, you would have to resort to a lot of synchronizations and a lot of locking and all these things in order, to avoid data races and stuff like that. So throughput and performance. So performance of platform threads, there is no problem with performance of platform threads. The only problem we have is the throughput. So we'll see why. Of course, it is also possible to do message passing concurrency in Java using a library like Akka or something like that, but the default is shared state concurrency, and that is where some of the problems and some of the complaints come in. So before we go into Project Loom and before we try to understand that, I think it is quite important to understand the current concurrency model. So OS threads or platform threads are at the core of Java's concurrency model. And it has a very mature ecosystem around it, but they also come with certain drawbacks. They are very expensive computationally, as platform threads are mapped one-to-one to OS threads. So that means every time you create a platform thread, you are paying quite a bit in terms of memory, in terms of computation, and all those things. Let's look at two of the most common use cases for concurrency and the drawbacks that the current concurrency model has for those. So One of the most common concurrency use case is serving requests over the wire using a server or a web server, stuff like that. For this, the preferred approach always has been a thread per request model, where every request is handled by a separate thread throughout, for its lifetime. So that's the thread per request model. And throughput of such systems can be explained using Little's law. So Little's law states that in a stable system, the average concurrency, or the number of requests that can be concurrently processed by the server, which is L here, is equal to the throughput, or the average rate of request, lambda, times the latency, or the average duration of average duration that is required to process each request. So basically, you can derive that lambda is equal to L by W, or throughput can be measured as throughput is equal to the concurrency divided by the latency. So in a thread per request model, the throughput will be limited by the number of OS threads available, and also by the amount of memory available for that particular JVM. So of course, OS threads are dependent on physical threads, right? So your CPU has a limited number of physical threads, and platform threads are dependent on that, and also dependent on the memory that is available. So there's a lot of limitations around this, and in order to increase the throughput, we often resort to workarounds or certain patterns. So the most commonly used pattern for that to work around this limitation in throughput is using thread pools or using asynchronous programming, and recently also using reactive programming. So these are kind of the workarounds that normally you do. Of course, you can also increase the hardware, the memory and everything to increase it a little bit, but there is always a limit for that. There is always a limit in terms of how much throughput you can achieve by doing all this. And all these workarounds also have their own limitations. For example, with thread pools, you have issues like thread leaking, you can have deadlocks, resource thrashing, and these kind of issues. And if you're resorting to asynchronous programming, which means you have to adapt to a more complex way of programming, because the normal thread programming in Java is quite straightforward. It's imperative, it's quite straightforward. You can use all of Java's niceties like the error handling, try-catch mechanisms. You can use your debuggers, profilers. Everything works very well with the normal thread model. But as soon as you switch to a asynchronous concurrency model, you would have to adapt your programming style for that. You would have to, you would have to kind of give up a little bit of all these niceties that Java provides in order to use asynchronous concurrency. Same goes for reactive programming. If you choose to do reactive programming, you would have to change the way you write your programs. You have to change your programming style. And you would have to introduce these changes in all the layers and everything. So there is a lot of work to be done for that, and also there are limitations. All these workarounds also come with their own limitations. For example, if you are doing asynchronous concurrency, you still have chances of data races. You still have to carefully make sure there are no data races. You still have to lock your objects. You have to synchronize them and all these stuff if you are sharing data around and stuff like that. Of course, there is also chances of memory leaks, thread locking, and so on. So that is the thread per request model. Another very common use case for threading in Java or in general is parallel processing or multi-threading, where you split a task into multiple subtasks and you kind of execute each of these tasks in a different thread. So this is to kind of it could be for variable different reasons. It could be to spread your load across. It could be to I don't know. It could be for I don't know like some sort of asynchronous setup where you have a lot of things going on. So you split them across different threads, so they all complete at the same time and stuff like that. So use cases could be different, but this is one pattern that is generally used. So I mean, if you go for the parallel processing model in Java, you still have to do a lot of work yourself. So you have to write solutions to avoid data corruptions. You have to write solutions to avoid data races in this kind of setup. Because if you're splitting a task into subtasks and if you're passing them into different threads, then you'd have to do a lot of thread synchronizations depending on your use case. You'd have to make sure that you're not corrupting data. If you're using the same database or same data source, you have to make sure you're not corrupting the data. You have to do all this yourself. So Java is not going to help you do any of that. You have to write this logic and guard logics and everything yourself. So the implementation, when you split the task into multiple subtasks spread across multiple threads, becomes very fragile, and it puts a lot of responsibility on the shoulder of the developer to ensure that there are no issues and there are no multi-threading related issues. So Project Loom aims to fix some of these issues. So the main two issues that we spoke about, the main two patterns that we spoke about, the thread per request model and multi-threading, the splitting tasks across threads. So these are the two main use cases that Project Loom kind of tries to solve. So it is by introducing two new features, virtual threads and structured concurrency. So this is the official description from Ron Pressler, who leads the project. So yeah, the aim is to drastically reduce the effort of writing, maintaining, and observing high-throughput concurrent applications that make the best use of available hardware. Of course, it doesn't explain a lot, but what it means. So let's look at them one by one. Let's look at virtual threads first, and then we'll look at structured concurrency. So virtual threads, aka user mode threads, aka coroutines, different names. I mean, technically async await is also a kind of coroutines. So different languages call these features by different names. So in Java, the final name seems to be virtual threads. It was fibers at one point, now virtual threads. So virtual threads are lightweight threads that are not tied to the OS, or the OS threads, but they are managed by the JVM. So you might be familiar of similar features in other languages like user mode threads or green threads or coroutines. Like Go routines, for example. I think Go routines is one of the most popular example of coroutines, and I think Go routines is one of the strongest selling point of Go language, right? And there is also coroutines in Kotlin, which is a similar feature. So this is a preview feature in Java 19, which means you need to enable the preview flag to use it and to compile and run it. So how does it differ? How does it differ from platform threads or the legacy green threads that we had? So unlike platform threads, the virtual thread implementation is managed at the JVM level. So the implementation is done at the JVM. So multiple virtual threads are mapped to one or more OS threads depending on the load. So these OS threads are called carrier threads, and a virtual thread can be mounted on one or more OS thread throughout its lifetime, depending on how often the virtual thread was parked. So for example, when you start a virtual thread, it could be mounted on, say, thread 1, and later it got parked. So when a virtual thread gets parked, it is kind of moved to the frames are moved out, they are parked, and the memory is kind of parked in the heap. And when this particular thread is activated again, it could be mounted on a new thread. So there is no thread affinity between virtual threads and the OS threads. So that is one main difference. And virtual threads, regardless of the number of virtual threads you have, the number of OS threads that will be used to mount them is decided by the JVM. You have no control over that. You cannot set affinity, or you cannot control those in any way. So they are all managed by the JVM. So it decides how many OS threads are needed for the number of virtual threads that you're running and everything based on the load and everything. So it decides everything. So and this is where it differs from the green threads that was the original threading mechanism in Java before platform threads. Because green threads, though slightly similar, the glaring difference was all your green threads were mapped to one OS thread, which obviously leads to thread starvation, because the more green threads you create, the more load on that one particular thread, and it's not going to scale. So that was the biggest disadvantage of green threads, which led to the replacement of that by platform threads. Because of course, with platform threads, you could have thread pools, and it could scale much better than green threads. So virtual threads are definitely suitable for thread per request programming style without having any limitations of the OS thread. So you can create millions of virtual threads without having to worry about your memory running out or your application crashing. So you don't have to worry about that, and you can gladly do thread per request. Without creating thread pools or without having to write any kind of mechanism around managing throughput. The JVM is going to take care of everything, and you're going to get excellent throughput. And with virtual threads, what we are trying to do is we saw Little's law, right? So in order to get more throughput, the only two ways to do is either increase the number of concurrent threads you could have, or reduce the latency. So with virtual threads, we are doing that, increasing the number of concurrent threads that you can run without having any limitations of OS threads or number of available physical threads or the available memory and so on. So you can, as I mentioned, you can create millions of virtual threads without affecting throughput. They'll be mapped to OS threads transparently. Of course, you could implement something similar with the current platform threads. I'm pretty sure there would be implementations where you're already doing something like that, where you are having a thread pool of certain threads, and then you are writing all this logic yourself to manage and park threads and everything to kind of increase throughput. I'm pretty sure there are implementations where similar implementations are done to increase throughput. But with virtual threads, all that becomes unnecessary. You could just switch to virtual threads and you get great throughput for free. And also doing this mapping and this implementation at the JVM level is much more efficient than doing it at the user code level. Again, as I mentioned, virtual threads are a preview feature in Java. They're pretty easy to use. So let's compare the virtual threads to Golang's Go routines and Kotlin's coroutines. So I think anybody familiar with Go knows what this is. So this is Go routine. They are pretty simple. They are quite easy to use, really powerful. And similarly, this is coroutines in Kotlin. Little bit more ceremony, but again, quite simple, powerful, easy to use. And finally, this is the new virtual threads, which I would say is closer to the one that we saw in Go. Of course, the syntax is different, but it's closer to the one that we saw in Go. So it is easy to use, again, flexible and powerful. As we saw, this is like code-wise for the exact same thing. It's as simple as any of the other examples. Developers can actually use virtual threads or platform threads as per their needs. So this is not replacing platform threads. This is going to coexist with platform threads, so you have both. The thread APIs are updated to support both without any breaking changes. Of course, that is what you would expect from Java. You're not, that's one of the strong suits of Java, giving you new features without breaking changes and stuff. Which means you can use everything that you use currently for your multi-threaded programming. Like you can use interruptions, your locking, parking, stack walking, whatever you're doing currently with your normal platform threads, you can also do them with virtual threads. So they are kind of interchangeable. So it becomes very easy to migrate or very easy to switch over. So these are the few other important aspects of the new implementation of virtual threads. So it is a thread, like the class. It is a thread class in code, runtime, debugger, and profiler. So if you look at virtual threads in any of these, from any of these perspective, you're going to see a thread. So it's a Java entity and not a thin wrapper around OS thread like what we currently have. It's a pure Java entity. Creating and blocking them are extremely cheap operations, whereas creating a platform thread is an expensive operation in memory and computation. So virtual threads should not be pooled because there is no purpose of pooling them. The only reason we create thread pools are to kind of work around the throughput limitations, right? Virtual threads, we don't have that. So you don't have to pool them, and you shouldn't be pooling them, because it will beat the purpose. So virtual threads by default uses the fork join pool work stealing scheduler. I think so. There are plans to add more schedulers, but for now it uses the fork join pool scheduler. You can use other schedulers. I mean, schedulers are pluggable, of course. So that means you can use other schedulers to kind of use virtual threads for asynchronous programming or other use cases. So that is a possibility, but by default it would be fork join pool. A virtual thread will always have its own stack memory, though the memory, like internally, it is mapped. The virtual thread memory is mapped to the heap, but when you look at from your code, it will have its own stack memory and everything. And the virtual threads API is very similar to platform threads, and hence, as I mentioned, very easy to adapt. So it's like it's not a completely new thing, or it's not a new API surface or anything. So that's the beauty of this implementation, because virtual threads are one of the biggest addition to the Java language, probably after Java 8. This is probably the biggest addition to the language, and this is probably the biggest change to the JVM itself, internally, how things work. So internally, a lot of change has happened for this particular feature. But for a developer, nothing much has changed. The API surface is so small that basically there is like few new methods and one or two new factories, and that's it. That's the only API surface for this huge feature. So that makes it extremely easy for migrations and for adoption. So let's have some fun with the threads. Let's try out some things. Let's compare how it performs with platform threads. So let's first see how many platform threads we can create versus how many virtual threads we can create on my machine, of course. So I have a Intel Core i9 with 8 cores and 16 threads with 64 GB RAM running Fedora 36. That's the configuration. So these numbers are going to differ based on the configuration. So if you are trying something like this, don't expect the same numbers. It's going to be different based on your machine. So let's try that. So let me make sure I'm using the right SDK. I think I didn't. Yeah, I'm connected. Yep. Okay, so let's look at the code first. So this is using the current platform thread. So we are just creating a thread and parking it. That's it. So let's see how many threads we can create and park. So let's run this. It's still quite a lot, I know. So it's going to crash. So let's see how much it managed to create. So around 32,000. So consistently, so whenever I run, I get around, I mean, not the exact same number, but somewhere around 32,000. So that's what this configuration is able to create. So you may be wondering how that is possible, right? Because I only have 16 physical threads, the OS threads. Well, it's because of multiple factors. One, Java has a very efficient and smart scheduler, which prioritizes unblocked threads over parked threads, and a little bit help from garbage collection. So if you were, if we were to run the threads concurrently, we would only get 16 threads, but we are not running them concurrently. So what the scheduler does is it kind of removes the parked threads and kind of schedules the new ones. So it kind of keeps going. Only problem being, every time a new thread is created, it's going to need some memory, right? So it assigns some block memory. And the problem is, once the memory is allocated, it cannot be resized. So at some point, you are going to run out of memory. Even though if the threads are parked, that memory is still blocked, so it's going to run out of memory. Also, like garbage collection is going to run and clear nodes that are not reachable from the root, so that's going to help a little bit. But again, it can only do this up to an extent before it runs out of memory, and it won't be able to schedule anything, and then it's going to crash. Because creating platform threads, as I mentioned, is an extremely expensive operation. and about the memory thing, so when a platform thread is created, most JVM implementations allocate more memory than it could require, because you don't want to run out of memory for a thread and end up in a Stack Overflow error. So the most implementation choose to give more memory than it might require. So in the end, you can only create so much. So in a way, the limitation or the limit for platform thread is the available JVM memory rather than available OS threads because of how the scheduler works. Let's okay. Now try the same with this is with the platform thread. Yeah, let's try the same with virtual threads. Okay, so the code. So this is the code. Looks quite similar except for this part where you are using a virtual thread. You are starting a virtual thread. That's the only difference. Again, we are creating a thread and we are parking it. So let's see how much we can do. So here I would have to pass in the enable preview flags. And I would also have to pass the source 19 flag for this to work. So immediately you can see the numbers. Those were in 32 like thousands, and immediately we are in millions. So it didn't crash, but it did slow down, right? I think 13 million or something, and it slowed down because it's waiting for, again, even for this also uses a little bit of memory, but way less memory than platform threads, but still is using memory. So it's going to wait for GC to kick in, free some memory, but it's going to keep going. It's not going to crash on you. The scheduler will wait for memory to be available, and once there is resources available, it's going to even keep on scheduling. So this is not going to crash. This will keep going. So I'm going to shut it down. Really? Yes, I have solutions. Yes. Okay, next, what? Sorry? Oh, I thought someone said something. Okay, next up. Now let's try some throughput experiments. So let's try creating 100,000 threads. Of course, we have the single thread executor. I'm not going to try that because, of course, 100,000 threads with a single thread executor, it's going to take forever. So not going to try that. So let's try the new thread per task executor. This is a new API added as part of Project Loom, but it has nothing to do with virtual threads. It's for normal threads, but just a new API to kind of to be consistent with the virtual thread APIs and stuff like that. Let's try the thread per task executor. So again, it is using the default thread factory, which uses the thread group. The APIs are already, so the APIs in JDK 19 are already retrofitted to auto close when you are in a try with resource block and everything. So we don't have to close them manually or anything. So let's try to run it. Okay, the code. So this is the code. So this is how you would do with single thread if you want, but I don't think there is any point in trying that because it's on one thread. So it's going to take the amount of seconds you're sleeping. So I'm sleeping for 1 second. That means it's going to take 100,000 seconds. So that's not a smart thing to do on demo. So let's try the multi-thread one. That is the sample that I had there. So it's creating 100,000. It's creating 100,000 tasks, and it's going to sleep for 1 second. So let's try with time. Task throughput. Oh, I hope I have the right one. No, I have the wrong one. Oops. Yep. Let's run it. So it's going to, yeah, this is about how much throughput we can get, right? So 100,000. I think it would be around 20 seconds or something, if I remember correctly. I think last time I run this, I had these numbers. So yeah, around 18 and 18 for the new. Yeah, kind of similar now. So that's the throughput that we got. So let's try a slightly different implementation. So let's try. So let's try the same, but with a thread pool. So here we are using a cached thread pool instead of the thread per task executor. So let's see how much throughput we can get. So theoretically, this should be better. And it was better. Like when I ran, it was better. Not by a huge margin, but it was still better than using task per thread executor. So as you can see, this ran slightly faster. So it is slightly better. But now let's try the same with virtual threads. Again, very similar implementation. The only difference being we are using a new virtual thread per task executor, as you can see here. So this one used the new thread per task executor with the default thread factory, and this is using the new virtual thread per task executor. Let's run it. Oops. That would have failed the demo, and it would have been wondering why it is not working. So this is going to be extremely fast. So this is magnitudes, order of magnitude faster than both the other example. Of course, all these can be further optimized. This is all like just simple examples with the most default implementations, right? And still, this is by far the most performant. So with more optimizations, this can be even better. So I also ran some JMH benchmarks with very similar code, and this is the results that I got. As you can see, of course, nothing much to explain. Virtual threads are the fastest, with thread pool coming second, and yeah, the thread per task is going to be the slowest, and single thread the slowest. But no point testing that. Again, this is a very simple benchmark. There are few other benchmarks that I found which does a bit more realistic use case testing. So there is one using Apache Bench, and there is one using Akka actors to kind of test the throughput. And there was another one testing the performance of IO and non-IO tasks, like doing web requests, doing file access, and stuff like that. So if you're interested, check them out. But short story is that you will find that virtual threads are outperforming platform threads by a huge margin in any of the benchmarks. I don't think you will find any benchmarks where this is not the case. So next is that's all about virtual threads. So the next important feature of Project Loom is structured concurrency. So structured concurrency aims to simplify multi-threaded and parallel programming use cases. So it treats multiple tasks running in different threads as a single unit of work. So it streamlines error handling, cancellations, it manages cancellations, it improves reliability and observability. So this helps to avoid the issues that we spoke about earlier. It helps to avoid thread leaking, cancellation delays, because normally when you use the existing executors to kind of split tasks, the biggest issues are thread leaking and cancellation delays. We'll see some examples of that. Please note that unlike virtual threads, which is a preview feature, structured concurrency is a incubator feature. That means you cannot run it just by adding the enabled preview flag or something. You have to add the modules, you have to run you have to add the incubator modules for that and everything. So that means structured concurrency might undergo more changes than virtual threads in the coming versions. So consider this example, which is using the current concurrent executor service. So we want update inventory and update order subtasks to be executed concurrently. So we have a faster overall execution for the handle order method. So each of those methods, like update inventory and update order, can succeed or fail independently. So ideally, handle order method should fail if any of those subtasks fail. That would be the ideal expectation. However, with the current implementation, and if this is your implementation, of course, in a real world example, you would have more guard logic and stuff around, but assuming this is your implementation, and if there is a failure, then things will start getting messy. So consider this scenario. So let's say update inventory fails and throws an exception. So I have marked all the failures in red, and like whatever is affected, I have marked in orange. So when update inventory fails and throws an exception, the handle order method throws an exception when calling inventory.get. So, but so far only update inventory failed and inventory.get, that part fails. But what about update order, right? So since it runs on its own thread because you're submitting it to a separate task, it can complete successfully. But now we have a issue with our business logic issue, right? Because we are going to have a mismatch between our inventory and order, because the inventory didn't get updated, but order got updated. That's not good. So when this happens, ideally what we would normally do is we would check for failures, and we would roll back the changes and stuff like that. So all this you have to do. You have to write all this logic to do that, right? So suppose update order is an expensive operation. Then when this failed, that expensive operation is going to continue to run, and it's going to continue to consume resources, which you don't want, because the handle order method failed already. So there is no point running this expensive operation. You could have saved that resource, right? So as I mentioned, in a real world use case, you would write lot of guard logic for this. You would write workarounds to kind of roll back things and so on. And let's take another example. So imagine update inventory is a long-running, expensive operation, and update order failed, because they are running concurrently. So even though update order threw an error, ideally we would like handle order to cancel update inventory so that we can save some resources, but that's not going to happen because the failure doesn't propagate through, and update order, since it failed, the entire thing is going to stuck on inventory.get because it is still expecting that to complete because it is a long-running operation. This entire handle order method is going to wait for that and wait until that happens. That is a waste of time for us. So another scenario, failure scenario, would be let's say handle order method was interrupted, some sort of interruption, whatever was the reason, though it was interrupted. So the interruption is not propagated to the subtask. Both update inventory and update order is going to continue running in the background. And when this happens, this is thread leaking. So the parent thread has been interrupted, but the child threads, they are still running, and they are leaking and running in the background. So that is waste of resources, a waste of time, and not a great error handling mechanism, because both your in a business logic wise, both your orders and inventory got updated, whereas your actual handle order failed. So whatever logic you had after that probably didn't work. So for these situations, as I mentioned, currently it's on the developer to handle these. You have to write a lot of logic to handle these kind of situations. So when you write these kind of implementations, you not only think about your business logic, but you also have to think about all these the language specific aspects, and you have to write logic to compensate for all these things that are not supported by the language. So this is where structured concurrency comes in, and this is what structured concurrency is trying to improve. Of course, structured concurrency is not going to magically remove all the problems that we have in that kind of implementations, but it is going to help. It is going to make the problems smaller, and it is going to make it easy for you to handle the other cases. So the exact same what we did previously, like this, can be achieved using the new structured task scope. So for the previous example, we used execution service. Here we are using executor service, and here we are using structured task scope to achieve the same result. What it does is, it confines the lifetime of the subtask to the lexical scope. And in this case, the lexical scope is the try with resource block. So that becomes the lexical scope, and the subtasks are confined to that. The code is much more readable, don't you think, like compared to this? You have clear intentions, you exactly know what is happening. and you know that there is a throw if fail, so you know that it's going to propagate errors and everything. So this is much more readable and much more concise. Let's now see what happens if errors, similar error happens. So structured task scope will ensure few things. So it will ensure that error handling happens with short circuiting. So if either update inventory or update order fails, the other is cancelled unless it is already completed. If it's a short task and if it completes before the other one fail, then there is nothing being done. But if it is a long-running task and if one fails, then the other is automatically cancelled, which is great. We don't have to write logic for that. We only have to write in case if something happened and successfully happened, we might want to write logic, but for most of the cases, they are automatically cancelled. So we are saving resource time, we are not having thread leaks. So this is managed by the cancellation policies implemented by shutdown on failure. You can also plug in other policies. There are some default policies, you can add more. Second thing that the structured task scope ensures is cancellation propagation. So if the thread running handle order is interrupted before joins are called, then those will be cancelled because the parent thread got interrupted, then the child task are also cancelled. So that happens automatically. And third thing that structured task scope offers is observability. So when you do a thread dump, it would clearly display the task hierarchy. It will show what threads are running. It will show what threads update inventory is running on, what thread update order is running on. It will be shown as the children of the parent scope. So you have a better visualization of what's happening when you are looking at thread dumps and stuff like that. Of course, as I mentioned, this is not a silver bullet which is going to suddenly make all of your use cases less fragile. You still might have to write some guard logic for depending on your use case. You still might want to check if check and roll back some changes at some points. But this makes it better. That's the point. This makes it better. You might be able to get rid of some guard logic that you have and let this new feature take care of that. So that's about structured concurrency. So the state of Project Loom. The project started in 2017, and it has undergone many changes and many proposals, name changes. The virtual thread feature was originally called Fibers. Then they were later renamed to virtual threads to avoid confusion, because I can see like Fibers doesn't say much. Virtual thread seems like better name definitely. And with Java 19, these two features are delivered as a preview and an incubator. So there is still a long way for stabilization, but it's already looking quite good. The performance already looks great. So I'm hoping the stabilization path is going to be smooth, and we will soon have these in production. So when these features are production ready, today it is not, but you can already see people starting to use it because of the great results. But when these are production ready, it should not affect regular Java developers, like people who are not writing libraries, for example. So it should not affect regular Java developers that much, because most of you might be using a library or a framework to handle your multi-threading needs, and those frameworks might be doing the migration for you. So you might just be updating to a new version or whatever. Like a web framework, for example. But it can be a big deal in scenarios where you are doing a lot of parallel processing in your application. You are doing a lot of manual concurrency without using a framework. Then it could be a great deal for you. And in those cases, migration could be pretty straightforward for you. You just if you are using a task thread pool, it's a no-brainer. Dump it and switch to virtual threads. It's going to give you better throughput out of the box, right? So virtual threads could be a no-brainer replacement for any use case where you're using a thread pool. It's going to increase the performance and throughput and scalability in most cases. Structured concurrency could also be useful if you're having a lot of parallel processing in your application. Few things to keep in mind. As I mentioned, the API surface is is very small, so easy to adopt, migrate. You will rely on the libraries that you use for some of the migration. Debugging virtual threads could be a bit different in the beginning to understand maybe, but you'll get used to it. You can easily switch to virtual threads from thread pools. You might have to do some unlearning though, because with virtual threads, you don't need thread pooling anymore. So you have to get that out of your mind. You have to unlearn that. And don't use virtual thread, with shared pool executors. Use the virtual thread per task executors. So you need to unlearn those kind of things. So you don't use regular executors. So, and virtual threads are so cheap, so you have to learn to start using them more. Because today, platform threads are expensive, so we don't think of threads for every use case. You only go for threads if it is really required, because we know the complexities around that. So we kind of choose. But with virtual threads, you don't have to do that. You can even use them for very simple stuff, like in Golang. In Golang, multi-threading is a second nature. If there are Go developers here, probably you know what I'm talking about. Multi-threading becomes a second nature to you, because you don't think too much. You just keep creating coroutines for everything, because they are so cheap. You don't have to worry about performance. You don't have to worry about these kinds of synchronization and these kind of things. So you create more use cases, or you convert more use cases to multi-threading use cases. So you can do that in Java as well with virtual thread. Even for short-lived simple tasks, you could consider using using virtual threads for that. So another thing to unlearn: don't reuse or recycle threads, because currently with platform threads, one thing that we do is we try to reuse and recycle threads because they are expensive. So you don't have to do that with virtual threads. Don't do that. Create new threads for everything. So avoid overuse of thread local, because thread local with platform thread is kind of like an ad hoc thread pool. You are kind of working around to make it a bit more efficient with thread local. Don't do that with virtual thread, because the more thread locals you create, the more threads you have, and if you're using thread local, then it's going to increase the memory usage. And if you are creating millions of virtual threads and if you use thread local, then that's not going to be nice. So don't use a lot of thread locals. Another important change, as I mentioned, is we would start seeing the proliferation of virtual threads in common use cases, which you might not be considering today, like in Golang. So probably using virtual thread will become a very normal thing that you will start seeing everywhere. And for libraries, so when these features are production ready, of course, it will be a big deal for libraries, because a lot of libraries can easily switch to virtual threads and increase throughput, get rid of current mechanisms that is being used for these purposes. So I would expect huge projects like Spring, Undertow, Netty, Tomcat, and Micronaut, and all these to kind of adopt virtual threads. I would also expect other multi-threading library like Akka, or all these libraries also to kind of adopt these and support these. I will expect those kind of support from libraries. Of course, virtual threads are going to displace asynchronous and reactive programming, because we do asynchronous and reactive programming as a workaround for throughput issues these days. So you can actually stop doing that and use virtual thread, because virtual threads are much more simpler to use than asynchronous or reactive programming, because those are complex patterns. They require a lot of work. They are harder to debug, harder to write. This is simpler, so it's easy to decide between these. So people are going to start using virtual threads instead of those. So the use cases for reactive and asynchronous is going to shrink. Of course, there will still be some use cases, but that's definitely going to shrink. So some projects have already started using or are planning to use these features. So I think Graal VM already added support for that. The PR has been merged. Quarkus already added support. Micronaut discussion is happening. Unfortunately, there is nothing solid that I found in the Spring ecosystem around this. I found some people trying some things with by kind of playing with the configurations and by providing their own thread factories and stuff. Of course, you can do it that way, but I don't see anything from the core. But I'm hoping there will be, because Spring also invested heavily in reactive programming. So now the question would be, okay, what do you switch the normal Spring MVC stuff to virtual threads and just get better throughput, or you? So there is that. Some more resources. Caveats first. So since it's a preview incubator feature, there's going to be some caveats and some issues, especially around tooling. I recently heard there was some trouble with profilers. Also, tooling folks have to work harder to start supporting this. You're going to see some tooling issues for a while until this is stable. So that's going to be some caveats. You're going to find edge cases, because this is preview and incubator features, not widely tested. So you're going to find some of that. There are already some chatter about some debugging weirdness here and there, some edge cases. So you are going to see those kind of things, but that is until these are stabilized. So that's to be expected from a preview and incubator feature, because that's the point of previews and incubators, to test, improve, iterate. Here are some more articles that I found quite interesting. So you can check them out if if you want to learn more about these. And if you want the slides, you can get these slides from here. And that's all. Thank you. And I'll be happy to take some questions. I'll be around here. Thank you.